I only have about 30 seconds to help you understand what this video is, because 30 seconds is about how long the median viewer watches. The median viewer means that if 99 people watch this video, and you lined up every viewer in order by how much they watched, we want to know how long the 50th viewer watched. In other words, this is the average viewer experience on my channel. I've also organized it by most popular and weighted it as such. If you've had a significantly different experience than what you're about to see, then congratulations, you're a fan. Alright, let's roll. Algebra. You may like it, you may hate it, you may have left it behind years ago, or you may still use it every day. But one thing's for certain, algebra is only the second subject in math that you learn after arithmetic. Therefore, it's pretty safe to say that humans agree that it's the second easiest subject in math. Let's learn it in 5 minutes. This is a variable. What makes it a variable is that it's not represented with characters that could imply a constant number. A variable is just a numeric value that we don't know yet. That's it. A variable can be written with any letter or character that isn't numeric, but most often we use x. Why x? Why not x? Variables also have a context. It is assumed that for every new problem, the context for variables are reset. Therefore, x will be one specific value for one question, and maybe another value for another question. But within that question, x remains the same value. It's also worth mentioning that using the variable x makes the use of an x as a multiplication sign very confusing. So, we'll represent multiplying two constants together with a dot or asterisk, and we'll represent a constant being multiplied by a variable with, well, nothing actually. A number next to a variable shows multiplication. Back when you learned order of operations, if you saw a problem that looked like this, you evaluated it in these steps. So, that means that the following problems are functionally the same. This introduces the concept of the equal sign, which implies that the terms on the left side of the equal sign are equivalent in value to the terms on the right side of the equal sign. Alright, let's learn some trigonometry, or algebra 3, or pre-calculus. Okay, lesson number 1. These are all the same thing. Trigonometry is algebra 3, trig meaning 3, and onometry meaning the study of. So how do we best learn about the number 3? Well, it takes half a year of relearning algebra 2, half a year of learning about the unit circle, and 4 seconds looking at triangles. Makes you wonder why they call it trigonometry. Anyways, remember pi? Here's e, his brother. E is the only number n such that the sum of k n's is a fixed r, and the product of k n's is a maximum given this fixed r. Okay, maybe that was a lot to think about. This is what it means. Imagine a bank gives you 5% interest every year, which never happens anymore, but go with it. So they give you 5% once a year. It's slightly nicer to get 2.5% twice a year instead. It's slightly better than that to get 1.25% 4 times a year. And you know what's way better than all that? Getting a tiny little fraction of a percent all the time. Every single moment. So you just get infinite money, right? Wrong! Turns out this is equal to this. Nature's a strange beast. So now it's January in the school year and we can finally learn about the unit circle, which is trigonometry at its core. Here's the unit circle. It's called a unit circle because its radius is 1, so the distance from the origin to any point on the perimeter of the circle is 1.
Introducing theta!
Don't be afraid, theta is just a variable like all the others, but instead of indicating how far to the right the point is, or how high up the point is, theta represents the distance rotated around the circle. Now, let's start at the point 1, 0 on the unit circle. There's nothing particularly interesting about the point 1, 0, except that the way that we decided to define trigonometric functions means that we have to start at 1, 0. You could start somewhere else, but then you'd have to change the way existing functions work. So, at the point 1, 0, you have rotated 0 degrees. At the point 0, 1, you have rotated 90 degrees. At the point -1, 0, you have rotated 180 degrees. At the point 0, -1, you have rotated 270 degrees. By the time you reach 360 degrees, you have rotated all the way back around to the original point 1, 0. Also, why are we using degrees? What's so cool about the number 360 anyways? Why don't we use a measurement that makes sense? Like the actual distance we've traveled along the circle. Well, it's a unit circle, and we know the circumference of a circle is 2 pi r. So r is 1, so the distance to travel all the way around the unit circle is 2 pi. So I'm just going to write these down real quick. X equals cosine of theta, and y equals sine of theta. So the cosine of theta is quite literally the distance to the right when looking at a point on the perimeter of the circle. Similarly, sine of theta is the distance up. So at the very beginning, when theta is 0, cosine of 0 is 1, because the point is 1 unit to the right. And sine of 0 is 0, because the point is 0 units up or down. Here's a graph. Calculus time! Calculus, or just calc, also known as the biggest barrier to cross over to the pure math zone, is the mathematical study of change. Specifically, it means change over the course of something. Most often this something is time, but it can be anything, like distance or time. Let x be time and y be the thing we want to measure. For a graph like y equals x, for every 1 we move to the right, we move 1 up. So the slope is 1. But what if we had a wacky graph, like this? Well, we can't answer that, but we can answer for the graphs like this. But first, we need to learn about limits. Limits are pretty boring when the expression follows usual rules of math. Limits are a way of making exceptions to rules. For example, we can't divide by 0, but with limits, we can divide by 0. Let's write out this limit as x approaches 0 of 5 divided by x. Technically, we're not dividing by 0. We're dividing by a number so small that it might as well be 0. This is what's called infinitesimally small. So what's 5 divided by a ridiculously small number? Well, if we divide by a small number, we end up with a big number. So the result is officially a really big number. We can't really say infinity is the answer, but infinity is the answer. Now that we've learned about limits, let's go back to graphs. We want to know what the slope is at any given point on the graph. This is known as instantaneous slope because it changes to something else the very next point on the graph. Let's look at a graph like y equals x squared. At x equals 0, we can figure out the slope by looking at the points just to the left and right. To the left, the curve goes down, so the slope is negative to the left. To the right, the curve goes up, so the slope is positive to the right. So we know that the slope in between the two must be 0, since the graph is continuous. Continuous just simply means that it's possible to draw the graph without ever picking up the pencil that you used to draw it. The graph on the left is continuous, the graph on the right is not. Any polynomial expression creates a continuous graph, y equals x squared being one example. But what if we wanted to get the slope of any point on the graph? To do this, we take the limit as x approaches 0 of a function evaluated at x plus h all divided by x plus h. That's a crazy way of saying we find the slope at that point. Now, the arithmetic involved with calculating this limit is very important, but it takes forever and gets old very fast. Instead, let's use some easy examples to take the derivative of y equals x squared. First, you look at each individual term of an equation. Here we have y and x squared. If the term is a constant, or has no variables, it becomes 0. If a term has a variable in it, we reduce its power by 1, and then multiply by that original power as a constant factor. So x squared, when derived, becomes 2x. 2 is the constant because 2 was the original.
Today we're going to talk about Algebra 2, and we've got a lot to cover, so let's get right to it. First, let's talk about multiplying binomials. A binomial may look like this, x plus 3. So then two binomials being multiplied together may look like this, x plus 3 times x minus 2. Notice how, even though there are two binomials here, they multiply two numbers together to create one number. So what would happen if we were to throw an equals 0 at the end of the line? X plus 3 times x minus 2 is equal to 0. Well, then this would be two numbers that multiply together to equal 0, x plus 3 as one and x minus 2 as the other. But what do we know about multiplying two numbers together and ending up with 0? Well, at least one of the two numbers must be equal to 0. So now, both of these equations are possible answers, leading to two solutions for x. X equals negative 3 and x equals 2. Two binomials multiplied together also assist in introducing an abbreviation that's surprisingly helpful, FOIL, or F-O-I-L. FOIL stands for first, outside, inside, last, and refers to the four multiplications that occur when multiplying binomials. As an example, x plus 3 times x minus 2 is x times x, which is x squared, plus x times negative 2, which is negative 2x, plus 3 times x, which is 3x, plus 3 times negative 2, which is negative 6. This gives us, when simplified. Notice that this end result is a trinomial. That means that, in some cases, we can start with a trinomial set equal to 0 and do the inverse of foiling in order to get two binomials multiplied together equal to 0. For example, if x squared plus 8x plus 12 is equal to 0, then we can set up a puzzle to find which two binomials this is as follows. First, we place the x's in the first position, since x squared is just two x's multiplied together. Then we fill in the other two spots by answering the following question. Which two numbers that add to 8 multiply to be 12? This works this way because the term with x is 8 and the constant term is 12. The outside and inside terms make up the term with x, and the last terms make up the constant term. Which two numbers add to 8 that also multiply to 12? Well, we can do this by listing all the pairs of factors of 12, and we conclude that the numbers are 6 and 2. And so x equals negative 3.
1, 3, 3, and 2, 4, 5, 1, 1, 1, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 90, negative 1, 0, 180, 0, negative 1, 270, 360, 1, 0, 360, 2, 1, 2, 0, 0, 1, 1, 0. So you may not know it yet, but you know base 10 already. Base 10 is called decimal. Deci meaning 10, and mul meaning base number system. But since it's base 10, there are 10 digits which you can use. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. After that, we need a second digit, a tens place. So let's say we wanted to use a different base number system, like base 6. Why 6? Why not 6? So, with base 6, we need the digits 0, 1, 2, 3, 4, and 5. That's 6 digits. Pause the video and count them if you don't believe me. So, how do we write 10 normally? Usually, we see it looks like this. That's because we have a tens digit followed by a ones digit. The only difference in base 6 is that it's a 6 digit followed by a ones digit. 6 in base 6 looks like this. 2 in base 2 also looks like this. 33 in base 33 also looks like this. In fact, every number in its own base number system is written like this. Why? Well, let's look at decimal one more time. This number is called 328. This digit means 3 hundredths. This digit means 2 tens. And this digit means 8 ones. If we look closer, 1 looks a lot like 10 to the power of 0. 10 looks a lot like 10 to the power of 1. 100 looks a lot like 10 to the power of 2. Continuing this, 1000 is 10 to the power of 3. So a 1 placed in a particular digit is the same as the base number to a power based on the location of the digit. So back to base 6. We call this the ones digit, or 6 to the power of 0. We call this the sixes digit, or 6 to the power of 1. We call this the 36's digit, or 6 to the power of 2. And we call this the... So question, what's 36 times 6? Cool, thanks, 216. Glad to know we can still do simple multiplication. So this is the 216's digit. Let's say we wanted to turn this base 10 number into a base 6 number. First, we see how many 216's we can take from it. We can take 1, so this digit is 1, and we have 112 left. From 112, how many 36's can we take out of it? Cool, thanks, 3. So 3 is the next digit. Så jag går ner i skiljer. Jag bara vad du snackar så svårt att hålla en effekt så att orkar en effekt det är ju håller snett det jag ska göra vad en så då nu här vad jag har nej ju han och du ska vara one för det snackar så mycket fina orkar snett det same ändå.